Assalamualaikum warahmatullahi wabarakatuh. So we continue with chapter number 5. Okay, so this chapter number 5 is only we are going to have only one lecture. Okay, lecture 1, because some of them are repeated but in SPS 4121. Okay, so we'll see the non-equilibrium thermodynamics and biochemical reaction. Okay, so we see first the second law of thermodynamics. So you are learning, I believe you learn this in your statistical physics, okay, or thermodynamics. Okay, so this is another approach for the second law of thermodynamics. Okay, so second law of thermodynamics is the entropy of an isolated system tend to increase. Okay, tend to become chaos. Okay, so for example, this one, entropy, a measure of how spread or dispersed the energy of the system is among the different possible ways that system can contain energy. Okay, so here we can see that there is a two compartment. So when we open this pipe, the molecule in this compartment will do the diffusion going to this compartment. Okay, so become average of these two. But if we have these two, okay, already filled with the gas or with the molecule, we cannot force the molecule back to only one compartment. Okay, it still will be in these two compartments. Okay, so we try to disperse itself. Okay, so the Boltzmann show that the entropy of a system is related to the natural log of the number of microstate. So again, this one from your statistical physics, I believe, or thermodynamics. Kb Boltzmann constant equal to 1.38 times 10 to the power minus 10 to 3 joule per Kelvin. Okay, S equal to Kb ln W, or in our textbook is Kb ln omega. Okay, so these are the microstate. This will be one microstate. All are in one space. In this state, so you can see that we have 4 microstate, and in number 3 we have 6. This one 6 microstate. Okay, so the ball red, blue, green, blue, green, blue, green, red, blue. Okay, so this one can make the move, this molecule can move to this compartment either by only one by one. So this is one microstate, and this also one microstate. Okay, so you can see that red, blue, green, yellow, green, yellow, red, blue, and so on. Okay, so we can count the microstate, how many microstate that we can have, so we can find the number of entropy for this system. Okay, so these are the example. Okay, the entropy. So hydrophobic interaction between non-polar molecule. Okay, so here these are the water molecule. Okay, so water molecule will uh, make a melingkungi ada this this polypeptide, hydrophobic polypeptide. Okay, so this polypeptide try to reduce the randomness. So if we try, or if we make into this micelle, lamella, or so on, so that it will feel the smallest force by the water molecule. Okay. Okay, and what we can see here is that, okay, so in animal and plant cell, so we have an open system. Okay, so meaning that the molecule can pass through a certain ion, or molecule can or pass through the membrane, okay, into the cell or outside the cell. Okay, so we're going to have, but this cell we try to reduce the uh, effect, okay, by keeping the inside and outside nearly the same. Okay, so here we can see that the energy formula to this biochemical system, again in biology, in SPS 4121 also we have this one. G equal to and even the statical thermodynamics we have, or statical physics we have G, this equation G equal to H minus Ts, where G is the Gibbs free energy, H is enthalpy, the heat content of the system, and S this entropy, the energy is the first dispersed within that system, a measure of the system disorder or randomness. So how random is that uh, system? Okay, and T is the temperature. Okay, and you can see here, if S increase, okay, so S increase, so H G will decrease. Okay, if S decrease, G will uh, increase. Okay, so we have this equation, or this information. Okay, so we just play with this number and this number, so we can get this Gibbs free energy. And as we know that even us, we love to stay at one place for a very long time. Okay, so it is comfortable for us. Okay, so this also for the molecule or biochemical system, or for the protein, we try to have a very low Gibbs free energy. Okay, so what we can see here is that if this delta S changing, delta H is changing, the enthalpy is changing, or delta S changing, so it will make the free Gibbs energy also changing. Okay, let's like say that if S is increasing, then delta G will be decreased. Okay, so here we have exothermic and endothermic. Okay, so exothermic reaction are accompanied by the release of heat to the surrounding, H final minus H initial equal to delta H. Okay, so this delta H. So this one also, if this decrease and this increase, this decrease, this increase, then delta G decrease. Okay, endothermic reaction absorb heat from the surrounding, taking heat from the surrounding, so delta H greater than 0. Okay, so as increase, if S increase and this increase, so delta G also decrease. Okay, okay, so here, in order for a process to occur, or for the reaction to occur, okay, the overall chain in free energy must be negative. Okay, so for A to become B, so delta G must be less than 0. Okay, so it try to move to the most uh, less energy required. Okay. So here delta G less than 0, then the spontaneous or exergonic reaction, for example A to B, so moving to right, produce more product. Okay, or R to P, so it will produce more product. But if delta G greater than 0, it's non-spontaneous or endogonic reaction, so moving to the left, so produce less product. Okay, or it will produce, or it will change, let's say in our biomolecule, so if we have the cis and trans. Okay, so let's say cis is A and trans is B. Okay, so if delta G greater than uh, 0, then we have a lot of biomolecule that is in cis conformation rather than the trans conformation. Okay, and for example, if in cis conformation, so it is not reactive. Okay, and trans conformation, it is reactive. Okay, so it will decide uh, the function of the protein. For example, the function of protein or the function of the nucleic acid. Okay, so here we have again the reaction. Okay, so this one is, let's say, changing from one molecule to another molecule, or one conformation to another conformation. So here we have unimolecular reaction, A changing to P, or producing the product P. Okay, so the rate of production of product, we can write it as equal to dA over dt equal to minus Ka. So we have K here, the rate constant. Okay, the rate constant from A becoming to P. Okay, so we can see how fast is that the production of the product. Okay, and if we solve this equation, this one is just first order differential equation from our math method. Okay, so the solution is a t equal to a naught, the initial value of a, to the exponential minus k t. Okay, depend on this k t. So here, these are the example. A is C4H8, become a product 2C2H4. Okay, so these are only unimolecular reaction. Okay, and again we have the A can become P, and P also can become A. Okay, so this one is just like say the, kalau contoh couple, tak couple, tak couple, tak couple. So we see this one. Okay, so here we have dA over dt minus K minus Ka plus Kp. For example, this Kp. So this can be we can found it in SPS 4121. Okay. Next is the biomolecular reaction. So we have biomolecular reaction. So we have triple molecular reaction to produce the product. So usually we have only two. So the reaction A plus B becoming P, bring a product. So one molecule reacting with another molecule, producing the product. Okay, so the rate of production is equal to dA over dt equal to minus Ka B. Okay, and again solving this equation. Okay, method of separation of variation of variation this math method in our math method. Okay, so this aka minus kbt. Okay, so solving this equation using the initial condition, so we are going to get this equation, or we can see that this for example this cb equal to uh, cb naught times ca over ca naught exponential cb naught minus ca naught of times k t. Okay, so we're going to get this value. Okay, and this one nampak terbalik this example. So these are A and these are B producing this value. Okay, or this one is an aqueous, these are liquid, and these are gas. Okay, so we can get this bimolecular reaction. Next, we have the redox reaction. Okay, so these are the example from our chemistry or electrochemistry. Okay, zinc solid, cuprum sulfate aqueous become zinc sulfate plus Cu. Okay, or in this case you can see that zinc plus cuprum 2 plus becoming zinc 2 plus plus cuprum. Okay, so we say that zinc is oxidized and cuprum is making the reduction reaction. Okay, zinc 2 plus plus 2 electron, cuprum 2 plus plus 2 electron becoming cuprum. Okay, so what we can say about this is that in our biomolecule, okay, so we can let's say the biomolecule is moving a signal from one molecule to another molecule. Okay, so we can see the speed and or the reaction of the between let's say A biomolecule with B biomolecule. Okay, so from that we can send the signal, let's say from our eye to our brain, or from our toe to our brain. Okay, so we can get. Okay, so here also we can use it this redox reaction. Okay, again this one electron transfer. So we send the signal, or we change the electron, or we can send the electron from one molecule to another molecule passing by the molecule. Okay, so we have this equation. Okay, P product is reactant. Okay, so P product become the reaction. Okay, oxidation, and R become reduction. Okay, oxidation, so R become reduction. Okay, so again calculating this activity, or the speed of the reaction. Okay, so these are just like this one. So solving this. Okay, so we are going to get this activity A delta G naught over Na minus KBT ln the concentration of R reduction, P oxidation, R the concentration of R, and P reduction. Okay, so we can also changing this into this energy. Okay, so energy, these are the initial energy, these are the current energy. Okay, so depend on the concentration of the this ion. Okay, so we can see that this can measure this ion and this concentration of this ion. So from this we can see whether the energy is greater than 0 or less than 0. Okay, so whether it's working, doing the doing the the work or not. Okay. Okay, and the theory of reaction rate. So these are in our SPS 4121 chapter, I believe chapter 4, no, chapter 7 and chapter 9. Okay, that is the reaction rate. And then if we want to speed up the reaction, so we can put the enzyme. Okay, so from the enzyme we can have this Michaelis-Menten kinetics. Okay, so this also discussed in chapter number 10, SPS 4121. Okay, but we what we want to put here is that we have the we can control the enzyme reaction or the Michaelis-Menten reaction by introducing the inhibitor. Okay, so let's say we have uh, one molecule. Okay, so we don't want that molecule to react. Okay, so we put the inhibitor, or we want to limit the reaction of that reaction. Okay, because if we put the enzyme, the reaction will be very fast. But let's say we want uh, the reaction to become much slower than the reaction without the enzyme. Between the reaction without the enzyme and reaction with the enzyme. Okay, so here we have a competitive inhibitor. Okay, so here you can see that the enzyme can take this molecule and this molecule. So if this one is taken by B, this spot is already taken by B, so A will not become active. Okay, so and next is the non-competitive inhibitor. Okay, so these are site for A and these are site for B. But if A is already attached to the enzyme, so it will inhibit B from attaching the enzyme. Okay, so these are the inhibitor. Okay, and this also we can see that in our COVID-19. Okay, so if the COVID-19 already attached to our cell, okay, so it will inhibit good molecule or good let's say the oxygen from attaching to this uh, cell. Okay, so that is the example of this our COVID-19. Okay, so we see this competitive inhibition. So with A and B competing for the same site on the enzyme, A plus E enzyme 1, 2, 3 is K1, K2, K3, the rate constant for this interaction. X is the uh, intermediate, enzyme intermediate. Okay, so R is the product, and these E are the enzyme. Okay, so here if A and B mixed with enzyme, so it will produce the product, but B with enzyme, so it will produce another product, Y. Okay, so here if we solve this equation, and this equation, so we are going to get the rate of reaction is equal to this equation, K3 CE naught CA CM. These are CE is the concentration of the initial concentration of the enzyme. A is the initial concentration of A. M is the speed of this rate reaction, and N is equal to K for K N. Okay, so if we see here, if N is, let's say N is high, okay, so N is high, so this become large, and this one become smaller, so the rate will become slower. Okay, the rate of production of R will become slower. Okay, but if Cm is, again, Cm is small, okay, Cm is small, then we can see that the rate of production of R is greater. Okay, so we are going to have this R. So what we want to say is that if K4 is greater than K5, okay, so we have and K4 is greater than K1, okay, so meaning that B is more reactive with the enzyme to produce the Y. Okay, so when this is more reactive than this reaction, so we're going to have less product, the R. Okay, so that is the competitive inhibition. Okay, so we have this rate constant. So if this rate constant is greater than this rate constant, then we can have a smaller production of R. So next is the non-competitive inhibition. And A attack on one side of the enzyme, B attack a different side of the enzyme, but in doing so, it stops the action of A. Okay, so here A, E, X, R, E, again, same, B plus E, Y, and B plus X, 6 and 7 become Z. Okay, so we have K1, K2, K3, K4, K5, K6, K7. So solving this equation, so we're going to have the rate of equation, the rate of production of R equal to this equation, okay, or this equation. So where Cm is equal to K2 plus K3 over K1, and equal to K4, K5, L equal to K6 and K7. Okay, so here we can see that if we say that L is greater than L is big, meaning that K6 is big, so this one will be smaller. Okay, so small, 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 and this one become larger. So we have the rate of production of R become much greater. Okay. Okay, so meaning that it cannot, L is greater than L is greater than N, Okay, so meaning that this A is reacting with the enzyme much faster than B. So all uh, the intermediate X. Okay, intermediate X. So B try to attack X, but not the enzyme. Okay, so meaning that A is this reaction is uh, dominating the reaction, so we can have higher production of R. Okay, this one. Okay, so that is the 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 topic for this chapter number 5. Okay, so what we can say here is that, or we can say here is that we can limit the reaction of the sum of the product or sum of the biomolecule, so that it uh, other reaction will be much fewer than the other reaction. Okay, and in this case, for example, if we have a virus, okay, a virus and antibody. Okay, so if the antibody can control or can react much faster with our cell, then the virus cannot attack our cell. So uh, our cell will be much safer, and we are not going to get much. We are not going to get sick easily. Okay, so I think we can stop here for this chapter number 5. Thank you. Okay, so this chapter number 5 only one lecture note.